Welcome back to Young Engineers of Today. First off, I apologize for being a couple of minutes late here, but we'll get started right on everything and get through as much of ancient engineering architecture as we can. As I heard, you guys actually already built your ballistas, which is pretty cool. I hope you guys enjoyed it. But we'll continue with this for a little while longer, and then we'll move on to the next subject as well, so that, everything lines up. Oh, and the adapter popped. Oh, that's no good. Oh, we haven't finished them yet. Oh, okay. I heard you guys had, but I apparently heard incorrect information. Oh, well, it happens. Whatever. Anyway, yeah, so we're going to continue with ancient engineering and architecture. Last we met, we talked about a whole bunch of Greek architecture, mostly temples, mostly the Parthenon, but the sort of some of the history of the design of temples and things like that that led up to the actual creation of the Parthenon and why it looks as it does, and the design motifs that went into it and things like that. So it was a lot of information all at once. Well, it wasn't. But anyway, so yeah, we spent all that time, and then we were about to get started on Roman advances. In fact, we talked a little bit about roads, but then we ran out of time. So as it goes. But yeah, Roman advances are of an entirely different nature from Greek advances at this point. Still engineering, but much less of a focus on structures and more so on infrastructure. And you'll see what I mean by that as we get further into it. But yeah, so just as a means of review, why would we name roads as an important part of Roman advancements? Like, why would that be a big deal? Well, it actually was a much larger contributor to the growth of the Roman Empire than you might think. The fact that they had the infrastructure that allowed them to travel between cities and towns and, allowed the military to move and defend their territory and things like that, that was actually a very important contribution to making the Roman Empire as large and as strong as it was. So for that reason, it's considered a pretty important, yeah, that wasn't just you. It's considered a pretty important advancement in history, despite how much we take it for granted now and how simple it seems. No, that was in the background. In addition, roads were surprisingly complex, considering. I mean, there were roads in a very strict sense of the term that existed before then, which were basically just dirt paths and things like that that denoted the distance and direction of different cities and things like that. But nothing like the roads that the Romans built, which were built specifically for easy travel and to last. You have a dirt or like a gravel path or something like that. If it rains somewhere along that path, it gets waterlogged and muddy, and that slows down travel. If there's, there wasn't really any snow of any sort, but over time that sort of erodes away at the actual road, and you get things like potholes and sinkholes and things like that, and that also slows down transportation, especially if, you're riding you're walking and you could potentially break an ankle and that kind of thing, and suddenly you're halfway to the city and it's going to take, twice as long to get there, that kind of a thing. Or you got horses pulling a wagon or something like that, and the horse breaks an ankle. Anyway, Roman roads were built to last. As you can see, there's multiple layers that go into the construction of a Roman road. It's got a lot of protection against the elements. In addition, it's got a drainage system which prevents it from becoming waterlogged, which again helps encourage faster travel along the roads. And for this reason, it was actually a large contributor to Roman civilization. And I showed this picture last Wednesday. This is a picture of a Roman road today, and it's still standing. I mean, it looks old, but it looks like it's been maintained all this time. Whereas it's entirely possible that it really hasn't been. It might have received some maintenance or something like that, but nothing, no real like resurfacing like we have to deal with roads today and things like that. So they were designed to last. Now, insofar as challenges are concerned with constructing a road, it's expensive. Certainly, for standards of Roman civilization at the time, it was work intensive. Same deal. Even for roads today, when we're creating highways that go between, major metropolitan centers and things like that across large stretches of land, they can be very expensive and work intensive to build. And we have machines that assist us with this. In addition, you have to worry about natural obstacles. A lot of Italy has a lot of natural hills and mountains and things like that, especially as you get, closer to really the anywhere. Italy is a very hilly place, and you have to basically answer the question, do I go around this? Do I go through it? If you go through it, you have to excavate through a hill or, build upwards or something like that. If you go around it, you have, depending upon the size of the natural formation, you have that much more road to build. So regardless, one way or another, you're going to have to deal with natural obstacles. And either way, it's going to make it more difficult to construct that road. And they did not use a compass or maps because those sorts of things didn't really exist in a sense that we think about them today. We can certainly, even like 30 years ago, we could use maps and compasses and measurement special measuring tools and things like that in order to figure out what direction the road's going to go in and everything like that. Nowadays we can use GPS and plot it out and use that in combination with special measuring tools. Of course, they didn't have any of that stuff back then. So as you can see, this dude here has got this thing that looks like a bunch of tea bags on a stick. It's really weird. But it was sort of it was a tool in order to ensure that the roads were built straight. And it was pretty remarkable because they managed to build such straight roads without a compass or maps. I mean, obviously there's that bend right there, that zag, but overall that is a very straight looking road. It doesn't have a whole lot of a curve to it that would suggest that that they didn't use any tools. They used a tool called a groma, which is that thing I was talking about. They're actually not tea bags; they're metal weights. But yeah, essentially you just placed a set of markers down the road. Oh, here we go. It was a square cross composed of two pieces of wood nailed together, right angles in all corners. So as you can see, it could be rotated. Each piece of wood had lead weights attached to the end, and a straight line was confirmed when one lead weight lined up with the one in front of it on the same piece of wood. So you'd look down it. If you could see, I don't know, let's use a different color, one that's easier to see versus this drawing. If you're looking down it and you see that this lead weight is obscuring this lead weight, you're looking down a straight line. And if it obscures all of the markers that they have set up, they know that they're building a straight road. So in essence, it was just a very simple mechanism to ensure that the roads they constructed were straight roads. And it did a very good job of that, obviously. If we're looking at this road right here, essentially eyeballing it, they were able to build roads that straight, which is pretty remarkable. Oh yeah, there you go. So yeah, the Romans built over 4,000 kilometers of roads. 4,000 kilometers. That's a lot of kilometers. In fact, hold on, let me do some conversion math here. In fact, it's 40,000 kilometers. I was off by a power of 10. $24,000 miles. It's 24,000 miles of road. Does anybody know offhand roughly how long it is from coast to coast on the U.S.? Roughly. Okay, well, it's about 3,000 miles, roughly. So that means that you would be able to go, the Romans essentially built a road that went back and forth from coast to coast on the U.S., what, 8 times? Yeah, 8 times. You can just turn down the volume on your computer. That should be the easiest way to do it. That's fine. But yeah, so coast to coast on the U.S. 8 times, which is pretty impressive. Again, considering they used this thing to just basically build roads by hand, laying everything with shovels and their own hands in baskets and stuff like that. That's a lot of roads. And as you can see, they run pretty much the entire length of the Roman Empire at the time, certainly at its height. So it was a big part of that. Yeah. All the way down into Africa. You've got, you know, Eastern Europe over here. Here, of course, is Rome and Italy. It went all the way up into the British Isles. It was down into Spain, and then, you know, through Spain to Africa, and then back all the way around the long way around the Mediterranean. Yeah, it's kind of crazy. Wait, that's not, that's the, yep, okay, I'm not crazy. All right, so moving on from roads, we have arches. You did call it. Um, I mean, I assume so. Arches added stability, strength, and beauty into Roman structures. Well, that's just kind of a generic line if I ever heard one. But I mean, the arches in themselves were also an architectural feat because um, just because of the way they're constructed, they actually used the shape of the arch itself in order to keep it together. It didn't have any sort of special stuff. Um, as you can see, there's actually a whole bunch of different parts to an arch. And everything has a name because we got to have a name for everything. But essentially, arches not only held themselves up by the way they were constructed, or by the way they were structured, they also helped support other structures. So any sort of archway bridge, any sort of you know, round tunnel, yeah, the Romans to thank for that because they were essentially the creators of the original arch design, which is pretty interesting. I mean, the way that the arch basically works is the way that all of the different forces acting on the arch essentially all cancel each other out. Because there's a downward force on the arch itself. However, the way it's structured is it distributes that downward force along the entire arch and down into the supports, And as long as the supports are strong enough to hold that weight, the arch stays standing. So it's a pretty ingenious design. Now, in addition, generally they'll need some forces that point inwards in order to keep the arch from, like, one of these things from just exploding outwards dramatically. But again, that's all part of the design of the arch. The arch was used in this little known thing. I mean, I don't know if you guys ever heard of it. It's called the Colosseum. It's no big deal though. It's nobody has ever really heard of it. It's not like it's one of the largest, freestanding ancient stadiums that ever existed. But yeah, it made extensive use of arches, as I'm sure you guys are well aware just by looking at it, to give it the strength to stand. Yeah, well, essentially, it's a lighter weight design than normal supports are, just by virtue of the fact that it's using less material, and the distribution allows less total weight for each support because, again, of the way that it's distributed. So yeah, the Colosseum was pretty big, 615 feet long, 510 feet wide, and it took 131,000 cubic yards of stone to make, which is a lot of stone. There's a lot of stone. Yeah, the house is haunted. That's why the door creaks. But yeah, 131,000 cubic yards of stone to make, which, depending upon your stone, I mean, obviously that's going to be many, many tons of stone. I can't do that math in my head right now. I apologize. But the Colosseum could seat around 50,000 people. It had gladiator games and mock battles and dramas. I mean, as we all think, the Colosseum gladiator games is very dramatic and outdated form of entertainment. Though, one that still fascinates us to this day as human beings. If from nothing else but just sort of an outside observer's point of view. But that was a big deal back in Roman times, gladiator games. It was their, kind of like their form of football. It was their form of entertainment. Then you have mock battles, and so that's, I mean, essentially just like Civil War reenactments and stuff like that. And dramas, plays. Old plays. And all that kind of stuff could be held in the Colosseum. It's like, yeah, it's like MMA, except very intense. This is kind of a cutaway of the Colosseum. It's not a terribly clear drawing necessarily, but it is one that is complete in the sense that it shows like a lot of the different structures that went into place in order to make, have the Colosseum standing, and the design philosophies and the design of it itself and things like that. The top of the Colosseum is going to have posts holding, the basically shades and flags and stuff like that. Then the top two tiers are wooden seating. So basically the discount seats, for lack of a better term, I guess. The vomitoria, which is the sort of the main area. Square windows and bronze shields. Basically the design that went into the top tier. The lower two tiers of the seating area are for upper class and the emperor and things like that. So obviously the best seats are reserved for the upper class. The emperor has his own podium, which is like his own box seat. But it's got special protection to ensure that, none of the gladiators try anything funny on the emperor. Trap doors to allow, people to escape and people to, be put into the arena and things like that, and animals and things like that. Beneath the trapdoor, you got the dungeons and the animals. So that's where they were all kept, and they were let up with the trapdoor, through the trapdoor, because there was a lift that basically lifted them up. Um, the stone construction itself was made out of several different materials, and the lightest materials were at the top. Obviously, they put the sturdiest materials at the bottom because those are going to be the ones supporting all the weights. And then as they moved upwards, in order to save weight, they moved on to lighter materials to help it keep standing. It's on a pretty solid foundation of rock in order to ensure that, the foundation doesn't sink and take the Colosseum with it, because that would be a big problem and, kind of hard to fix, because you would have to fix the ground underneath an already standing structure. It's kind of hard. Although there were still issues with it because it was different rock types. The south face actually suffered earthquakes, which is pretty interesting. I didn't actually know that. That's kind of crazy. You don't want to sit in the south face. But yeah, so there was a lot that went into the Colosseum. And finally, one of the other things that used arches and was certainly less noteworthy than the Colosseum, when you think about it, but no less important to Roman civilization were the aqueducts. Because not everywhere in Rome, in the Roman Empire, had water, easy access to water. But there were places that were strategically important to live. There were places that, to have troops there and stuff like that. There were places that, had people there already, and so they wanted to take care of the people and improve their quality of life, even if it's just from, a PR standpoint. There were, places where people just set up there anyway, and they were like, well, okay. So for that reason, they utilized things like aqueducts. It also allowed them to fertilize crops and grow crops in areas that wouldn't traditionally grow them. And obviously not as well as the more fertile areas of Rome, but it did enable it. Well, why do they need to bring water in? Well, there was not enough water from the city's original source to meet Rome's demands, Rome itself. So Rome supplied water to private homes of wealthy and those peasants who could afford the charge, and also a plethora of public baths, fountains, and public toilets. Oh, there you go. That's actually another major reason. There was a lot of aqueducts for Rome itself because they wanted to have as much water as possible. They wanted a lot of water, not only for drinking, but also for cleaning. Yeah, there's that too. But that was before people were really savvy about it. Like, they liked clean water, but they didn't think necessarily that, like, it was going to ruin everything. Um, yeah. Besides, you can always grab water from upstream and then deposit water, among other things, downstream. So they built 11 aqueducts in total between 312 BC and 226 AD. You can see this nice little GIF here. Cavity, yep. Archways, everything ran downhill. Stonework, keystones, water. Yep, that's really fast to read. But yeah, so basically workers dug channels underground and created networks of pipe to carry water from the outer source of the Tiber into Rome. And the pipes were typically concrete, but sometimes they were lead. And then siphons were used to create enough momentum when the pipes had to span a valley. So basically what that was they just, when it had to go through a valley, they stuck the pipes underground. So the water had to drop so far, so fast, that it had enough momentum to make it back up the hill. So it just go, and it go really fast and then slow down again, but make it to the top and then be able to continue along its merry way on the aqueducts. So yeah, that's just a bit of the structure of it. Now, of course, why didn't they just do bridges everywhere? Well, because, it's not always feasible to put bridges everywhere uh, because it's expensive and it's labor intensive, just like the roads were. And in addition, if it didn't dip that much, they could use a siphon in order to get across it. Oh, well, there you go. Differences between a modern aqueduct and a Roman aqueduct. You've got the reservoir and the intake, just like you do in a modern one, and then it travels along the conduit, down an aqueduct bridge, and into the city. Now, what we do is we use a siphon, essentially, in order to be able to, transport that water to the treatment plant, because we do love our clean water, understandably so, and then it goes from the treatment plant to the city. But yeah, so the same basic idea, except we just utilize siphons, which again, thanks to the Romans. And that's an aqueduct in Minecraft. Okay, so that actually does it for architecture. Let us... Let me do one more pass to see if I can't find that ancient architecture weaponry one. I've been looking for it, but I haven't had any luck. But I might have just missed it. I don't think that's it. This might not be it either, but it's worth a look. Of course, everything's worth a look. Guess that's not a whole lot. Aha! We use this one. Just because it might be listed as an old one, but this goes over a lot of different advancements in ancient engineering insofar as war machines are concerned. So it provides a lot of the history that leads up to things like the trebuchet. So we'll use this one, catapults. That was my issue. I was looking for a different name, and also one that was not labeled Old Ancient Engineering. Anyway, the part of this was you guys would be building stuff alongside it. That's since you're doing the ballistas in a lab, we won't be doing that ourselves. But there's it's still got a lot of good information in it. So insofar as catapults are concerned, catapults can be split into three categories. You got a traditional catapult, which is the one you generally think of. You got a ballista, which is the one you guys are building, and then you got a trebuchet, which is a third type, which is actually pretty awesome, and you've probably seen trebuchets before. But a traditional catapult looks like a bucket on a long arm being held down by some form of tension. I mean, the one you think of when you think of catapult. A traditional catapult uses stored tension by twisting and stretching ropes or bending wood to vault its mass into the air. So essentially, this is the arm of the catapult. Like if I were to extend this drawing a little bit, this is where the bucket is that holds all the stuff. Look at that bucket. What a beautiful bucket. And they twist this material. So essentially, it stores up a whole bunch of tension energy. And then when you release it, all this stuff spins like crazy fast, releases all that energy, the bucket goes up, and the stuff gets launched. In essence. So yeah, a traditional catapult can store more energy to send their projectile further by using a winch, which means that you can... So in this particular one, as you can see, turn the handle to tighten. At some point, you're going to not be able to make a catapult any stronger because people aren't going to be strong enough in order to arm the catapult. Like, it's going to be too difficult to actually arm the catapult. So what you can do is you can utilize things like winches, which utilize wheels and axles, and in a sense pulleys as well. And they can actually increase the and levers, and they can increase the basically the relative strength of a human, so that they can winch these stronger catapults and arm them. Yeah, tension energy. So then you got ballistas, which you guys are familiar with. They look like a giant crossbow. So like a catapult, as you guys know, a ballista works using tension stored in string and wood. You can think about a ballista working similarly to a bow and arrow, but with additional energy stored in twisted ropes. So, pulling winching everything back as well. There's some energy stored there as well. So yeah, unfortunately, war has always been a motivating force in the development of new technologies, and that's still true into today. That has always been one of the things that war can provide. I mean, we've got things like radio, and by extension, Wi-Fi, and GPS, sort of. Although it's just the transmission of the information, Bluetooth, cell phones, all that kind of stuff. That's all thanks to the advent of the radar. A lot of medical technologies are thanks to wartime advancements. A lot of the food we eat today actually is thanks to wartime advancements. Insofar as microwave dinners and things like that, a lot of those are actually based off of the sort of the structured approach to meal creation for soldiers, like MREs and things like that. And then it got kind of adapted into TV dinners and lean cuisines and things. Tyson Chicken was actually a major player in supplying food for soldiers in World War II, and then they turned their eye towards the American public after the war was over. So, if you've ever had anything by Tyson Chicken, well, they got super successful from World War II. Obviously, there are a lot of advancements that don't come from war. Things like Teflon and windshield wipers and instant ramen and things like that, but makes it sound a lot more useless. But anyway, that's actually been a huge driving force in technological advancement. So the history of the catapult goes like such. This. In 399 BC, Dionysius of Syracuse wants people to design and build weapons for his campaign against Carthage. So he basically creates a think tank, a group of people meant to brainstorm ideas for him. And they wanted to overcome the limitations of the basic bow and arrow, because here's the problem. So basically the way a bow works is tension energy. So it experiences compression on the concave side, which is the inside of the wood on the bow, and then tension on its convex side, so on the outside of the bow. And the release of that tension and the compression, propels the arrow forward, as we all well know. This does not have, yeah. So imagine a loose rubber band versus a taut one. Imagine letting go of that rubber band and you have some idea of So potential energy is stored in the rubber band, just like potential energy is stored in the bow when the bow is drawn. As you pull on the string of the bow, your arm does the work, and then the energy that it takes you to pull that string is stored in the bow as tension. When the arrow is released, elastic energy transfers to the kinetic energy of the arrow. So basically the tension and compression force gets transferred to the arrow in the form of kinetic energy. And then you shoot an arrow. Boop, 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 boop. So the ability of a bow depends on its ability to store that energy. Basically, how strong a bow is depends upon how well it can store energy inside of it. More energy stored translates to higher velocity of an arrow when released. Makes sense, right? So basically, the stronger the bow is, the harder it is to draw. However, the more energy it will store, which by extension means the faster that arrow will go when you let go. So the bow must be strong enough to carry the maximum pulling force without breaking. So what does that mean in terms of improving design? Well, bow makers discovered that they could strengthen the bow even more if they combined wood, animal horn, and animal sinew. So basically, wood and animal parts. They increased the power of the bow. Oops. So horn holds up better to compression, so it was added to the inside of a wooden bow, while sinew holds up better to tension, so it was added to the outside. And so both of these increased the strength of the bow, which meant that it could store more energy and you could exert more force on the bow, which meant a faster shot. And this was the compound bow. And I'm sure you guys, if you've I'm sure at least some of you have heard of the term compound bow before, and all it essentially just means is a bow made of multiple materials in order to better store energy. So the compound bow was wildly successful, very, very successful. In fact, so much so that the limitations on the strength of the bow were physiological. Now, based on that, can you probably guess what that might be? People being bad at aiming. That's a good one. I mean, yeah, definitely. But people did train all their lives to be able to aim. Yeah, there you go. Yeah, that and another thing. There was actually a second thing. So the first one was people weren't strong enough to pull it back. Because at some point the bows became so strong that people couldn't, actually easily pull them back. So they had a limitation in that sense. They could only make the bow so strong because they had to have the user be able to pull it back. And then a second one. Think about the bow would shoot backwards instead of the arrow shooting forward. That would be quite the thing, and that would probably end poorly for a lot of people involved. Although think about, hmm, you could store more energy by making a bow larger, right? Yeah. At some point, humans we ran into another limitation, and that was basically the average human arm span. There was only so far you could draw the bow back because there's only so long our arms are. And also the strength and dexterity of the fingers. Because obviously you could have arms that are strong enough in order to draw a bow back, but it could really hurt your fingers to do it. And it might be hard to hold on to that bow, which would reduce your accuracy and, potentially put you in a situation where you accidentally let go of the bow sooner than you wanted to because, it just, your fingers give way, which is potentially catastrophic. And then, yeah, length of arms and everything like that. So because of these limitations, the best possible bow required 45 pounds to pull with a 28-inch draw range. Any more than that, it couldn't be any more poundage, and it couldn't be reliable. Any larger than that, and they couldn't guarantee that people were going to be able to draw them back all the way. Now, granted, there are heavier bows that exist out there in the world today, but from the perspective of being able to use them regularly in a battlefield environment, anything more than 45 pounds just became unwieldy. Oops. So how is this think tank, in essence, going to advance bow and arrow technology? Well, their first solution was the Gastraphetes, or the belly bow. Doesn't really look that much different, right? But there's not a whole lot of perspective here. This might help. It was big. You, in fact, used your entire torso, your midsection, to load it. Well, you put your legs into it and everything like that. But yeah, basically you pushed it down with your midsection, which essentially, cocked it like a crossbow. And this meant that they could increase the force by about 3 or 4 times as much as they were doing before, because you would be able to push it down and load it that way. Suddenly you had just monstrous, handheld bows. The draw length was also determined by the length of the weapon, not the length of your arm anymore. So it solved 2 problems in one. Using your entire body meant that you could exert more force on the bow to draw it, and using your entire body meant that you could make the bow larger so that you could store more energy that way. You weren't limited to just the length of the arm. And it had a ratcheted design, which ensured that it didn't accidentally go off. And you could also control the force of the draw, so you could only ratchet it up like 3 times, if you wanted a weaker draw or something like that. Or you could go all the way up to maximum power if you wanted, a supersonic arrow. And then there was a trigger mechanism, much like a crossbow, except it's sort of an ancient version of it, so it's not as what's the word I'm looking for? Elegant necessarily. It was just a big latch. Then you just knock the latch back, and then the thing fired. So weapon makers continued to improve upon the Gastraphetes. Well, what did they do to make it better? Well, they made it bigger, of course. This development led to the technological advancements that made the first true catapult possible. So stiffer bows made cocking the weapon more difficult. This was Zopyrus's bow machine. As the Gastraphetes got stronger, it became harder and harder to cock the weapon, even with your whole body. So then they started utilizing basically a pulley and wheel and axle system in order to cock the arrow. This allowed for larger arrows, but on the other hand, the weapon was becoming so large that they needed to add a base to it so that you could actually, steady it and everything like that. But the size of this thing, again, we're talking about like a person is, let's see here, probably about this large in relation to it. Whoop. There's their hands holding onto it to wind it up, and then the legs. Like, it was a big machine. So they added a base to it anyway, because it was so heavy and large that it wasn't something that could be reliably held to fire. That was 7 feet. Oh, wow. Okay. Bows on this first model of catapult were maxing out the size that artisans could make them. So we were rapidly approaching the limit of, the regular bows. So composite bows temporarily meet their limits. Developers must now turn to a fundamentally different way of storing elastic energy, and this path led to the Torsion Catapult. So Torsion Catapult development occurs over a series of discoveries and advancements starting in the mid-4th century BCE. By the end of that century, we have the arrow-shooting weapon called the Euthynton, and the stone-throwing weapon called the Palintone. As you can see here, this doesn't really provide justice to how large these things were. they could have been over 45 feet in length. Like, it was possible that there were some examples of them being over 45 feet in length, which is just absolutely ridiculous. That's just a gigantic machine. But much of the hardware looks the same as the Zopyrus's bow. So you got the stock, the ratchet, the trigger, the windlass, and all that kind of stuff. But what's new are vertically aligned torsion springs. And essentially, the torsion is the twisting of a beam or structural element. That's how you can create stored energy, is a torsion. By twisting something, it wants to return to its natural untwisted state. So torsion springs became the primary storage for elastic energy in this device. I say what used to be, this says what used to be the primary storage, but you guys have memories longer than 5 minutes. So, it was compression and tension. And torsion springs in a palintone consisted of bundles of rope with a wooden arm thrust through the center. So as you can see again in this illustration here, there's a whole bunch of ropes as these are actually the arms. So if we go back to this design right here, that next drawing, or that next picture, is like looking at this part of the palintone. So as you can see, the arms are peeking off to the side here, and here are the rope coils. So there you go. Got the arms coming off to the side over here. And they're all hooked up to their, the arms. But yeah, those cords of those knots of rope would twist and store up torsion energy, and that would be the mechanism for firing. Well, that would be the mechanism for storing energy to fire. Oh, there you go. It's actually a better illustration. Here's actually that housing for each of those bundles of rope. Oh, it doesn't want to play that. But anyway, yeah, it would be pulled down and it would twist this entire mechanism, and the rope would twist, and it would be storing up torsion energy. So there are reports of arrow shooters that could shoot 200 yards and Roman ballistas that could throw 200-pound stone balls 400 yards, which is really far. 600 feet and 1,200 feet. That's a lot of stored energy. Imagine how fast they're going too when they first come out. So the torsion catapults were so important for city defense, walls were made thin to support arrow shooters on the inside. So they actually changed the structure of, the city fortifications so that they could enable these things to exist within, the city wall. It totally went counter to, the design philosophy in the past, which was to make the walls as thick as possible to, prevent arrows and stuff like that from getting in, and, make them as high as possible. And so now they provide windows for the, well, they make the walls thin, and they provide windows for these arrow shooters on the inside. The design of these machines also led to huge strides in math and engineering that helped not just the military sector, but transferred to the civilian, as engineers grew to better understand the mathematics behind their designs. Impressive developments occurred, including what? Okay, it's the same slide twice, and one of them is misspelled, and one of them was not. Oh, they must have gotten rid of that one. Oh, fair enough. Anyway, you got the Scorpion, the Chiaro Ballistra, and the Hatra Ballistra. Or that's just a ballista. I feel like this should be a ballista as well. The Scorpion had forward curving arms, and the Hatra had backward curving arms. The Scorpion had 2 forward curving arms, and the Hatra had which basically reversed the tension and the compression energies, and how they were distributed on the uh, weapon versus the direction the arrow was going to be fired. The Chiaro Ballistra, I guess it is the Ballistra, had an iron frame, and the torsion springs on the inside were encased in bronze in order to prevent them from fraying and everything or being shot at. And then the Hatra Ballista had inward swinging arms, and they could rotate through a significantly larger set of arms. All of these advancements, I mean, all of these ideas were eventually applied to the traditional catapult. Basically, the transference of the torsion energy to a much larger arm, a fulcrum of a much larger arm, and then adding, the winch in order to help arm it, meant that they could launch much larger things much further, because a lot of that energy was being transferred to a larger arm. It wasn't quite as efficient just because the arm was so heavy, and the bucket just sort of flung it, so it wasn't as accurate as either of these, but it was very easy to maintain, and it was very simple to build. And so this was the advent of the traditional catapult. Anyway, that's going to go ahead and that's going to do it for today. We'll move on to trebuchets on Wednesday. We'll probably spend at least a decent part of the class going over that. Hopefully we'll be able to fill it out with at least something else if we don't happen to get all the time, or if we have more time than is necessary for the presentation, I'll figure out something else as well. But yeah, that's going to go ahead and do it for today. Let me go ahead and do the poll questions, and then we'll leave it open for question and answer time, and then we can go ahead and just break for the next couple of days and meet up again on Wednesday.